So in our very first section, we learned about that difference between tangent and secant lines. So if I have a particular point here, say at C, that tangent line is just going to touch at point C. While my secant line, say here at some point X, connects those two pieces. So my secant line will cut through these two, okay? The tangent line touches at a single point, while the secant line connects 2 points on the curve. So we spent this time learning this limit process because what ends up happening is if I let this X value get closer and closer to C, we're actually gonna notice that the secant line approaches this tangent line. So let's look at kind of just a picture with an example graph. I've got my tangent line here at C, and I want to go ahead and find the secant lines between this particular point and all of these other ones, okay? So first, if I go through this point that's furthest away, that pink one, that's going to give me a tangent line, or an approximation that's not so great to the tangent line. But if I push this point inward and get closer to C, the Y value would be up here. Connecting those two dots, I get a better looking line. If I let X get even closer to C, and I go ahead and connect the green and the yellow dots, this secant line is a much better approximation for the tangent line. So if I consider a point nearby where I'm looking for the tangent line, I can go ahead and get a decent approximation. And I know how to actually calculate that slope, because the slope of our secant line is just the difference in those Y values divided by the difference in X values. So to get the slope of this actual tangent line, I'm gonna let X approach C. So we're ultimately going to be taking a limit. So we let X approach C to get the slope of our tangent line. Okay. So our formal definition, the tangent line to the curve y equals f of x at some particular point is the line that passes through this point with slope m, which is defined by letting the limit as x approach C of the slope of our secant line. Of course, provided this limit exists. So it's possible that it might not, but in the case it does, this would define our slope of the tangent line. Okay. So let's try an example utilizing this definition. Ultimately, this one's not going to be the best one for us. We're gonna see another expression very soon that's gonna be much better. So we wanna find an equation of the line tangent to y equals x squared at the point P, which is 2, 4. So if we plug in 2, we get 4. Kind of matching up with our definition, our value of C that we're approaching is 2, and our function is equal to x squared. So when I go to actually find my tangent line slope, it's going to be the limit as x gets closer and closer to 2 of the difference in our y values, which is our function, minus the y value corresponding to 2, divided by x minus 2. So this is equal to the limit as x approaches 2. Our function is x squared. The y value corresponding to 2 is 4. And in the denominator, we have x minus 2. So this gives us the limit as x approaches 2. We can factor that really nicely. X plus 2, x minus 2 over x minus 2. With some cancellation, this gives us the limit as x approaches 2 of x plus 2. And 0 problems plugging that in now, we get 2 plus 2 or 4. So ultimately, my line passes through 2, 4 and has slope 4. So the tangent line is y minus the y-coordinate of the line is equal to the slope times x minus the x-coordinate. So that's y minus 4 is equal to 4x minus 8. Adding the 4 over gives us the tangent line is 4x minus 4. Okay. So this process is quite tedious, trying to go ahead and calculate this slope for every single point, calculating a limit. It is difficult. So instead, I don't really want to go through this process where I'm finding the slope at a particular point. Instead, what I want to do is look at a second expression that's going to be a little bit easier. And it's going to give us a more general approach in a few minutes. So really, there's a second expression that will be easier for us to work with. So our goal is we want to find this tangent line. And I know it's going to be the limit of our slope of the secant line. So what I'm going to do is I'm still going to calculate the secant line, but I'm going to look at it a slightly different way. This is what we were calling our x value just 10 seconds ago. Instead, what we've really done is we've started at C and we've added some distance. I'm going to call that delta x. So really, this x-coordinate is C plus some small change. Okay? So we're going to fill in a nice little right triangle to look at our difference of x's and our difference in y's. Okay? So my change in my x values, we're calling that delta x. This point here then has x-coordinate C plus delta x. The y-coordinate would be you plug in C plus delta x into the function. So to find my slope, which is my rise over my run, I need what this quantity is, and it's just those difference in the y values. So we're going to look at the difference between these two quantities. So my change in y is going to be my function evaluated at C plus delta x minus my function evaluated at C. Okay. So ultimately, as we let this change get smaller and smaller and smaller and smaller, that's going to still make these 2 points super close together. So as C is approaching, or as x is approaching C, my delta x, so my change in my x values, is approaching 0 to make these 2 points right on top of each other. So really, an equivalent expression for my slope of the tangent line is the following. My slope is going to be the limit as x approaches C of the slope of my secant line. But really, the slope of the secant line is the change in y over the change in x. So it's the limit as delta x approaches 0 of my change in y over my change in x. But all that is in terms of the function is the difference in these y values divided by the difference in the x values, so that delta x. Okay. So this is another equivalent expression. I'm going to go through an example because WebAssign's going to ask you some questions similar to this using this notation. But really, there's a much cleaner approach that I'm going to show you afterwards. So now, using this definition, we want to find the slope of the tangent line to the graph of g of x, which is 5 minus x squared, at this particular point. Okay? So again, our value of C in all of these places is that x-coordinate we're finding the tangent line at. So it's going to be 3. So I need my slope. Using this definition, it is the limit as delta x approaches 0 of my function evaluated at 3 plus that small change, my function is g, not f, minus my function evaluated at 3, divided by the difference in these x values, which is delta x. Okay. So plugging this expression in for x gives us the limit as delta x approaches 0 of 5 minus 3 plus delta x squared. And then when you plug 3 into the function, you get -4 in return. And that is divided by delta x. So I want to go ahead and keep working with this expression and hopefully make this delta x disappear, because I can't plug in that at 0 right now because I will divide by 0. So we've got to go ahead and FOIL this top piece out. I'm going to worry about distributing the minus sign afterwards. If you take 3 plus delta x squared, that would give you 9 plus 6 delta x plus delta x to the second. And then minus 4 gives you a +4. And then all divided by delta x. Okay. So we keep going. Distributing that minus sign gives us 5 minus 9 minus 6 delta x minus delta x squared plus 4 all over delta x. And if you add these up, that would be 5 minus 9, which is -4, plus 4. Really, all of these end up canceling. And so this is the limit as delta x approaches 0 of -6 delta x minus delta x squared. Okay. Now everything in here has a delta x. So we're dividing by that quantity. This completely cancels, and only 1 cancels in the square term. So we are taking the limit as delta x approaches 0 of -6 minus delta x. Now you have 0 problems plugging in delta x is 0. So the slope of this tangent line is -6 minus 0, or just -6. Okay. So this process really leads to our first major operation. We are not going to sit here and find the slope every single time in this manner. That would be way too tedious, way too disgusting. But this idea of taking limits is important to us. Okay? So this process leads to our first major operation, which is differentiation. We could continually calculate the slope of the tangent line at every single point through this process, but it would definitely be really tedious. So instead, we can change our viewpoint and let this value of c vary. So in that equation I have way back up here, instead of dealing with this particular point c, we're going to replace that by some value x. So this tells us the slope of the tangent line at an arbitrary point, x and y value, can be given by this. And ultimately, I'm not a fan of really using this delta x. I like putting an h instead. So instead of using this delta x here, here, we're going to replace it by h. Because you have calculated that difference quotient over and over and over again in all of your prior classes. This is why you have calculated that difference quotient, because it gives you that slope of the tangent line, okay? But this tells me my derivative at any point I want. So I'll come up with a function in the end instead of set numbers for slopes. And that function is going to tell me what the slope of the tangent line is at any point. So this is what's formally known as our derivative. The derivative of a function f at any point x is given by this expression, where I'm going to take the limit as h approaches 0 of that difference quotient, which is really just the slope of the secant line between 2 points. Okay? So this is really nice. This is our first big idea, that this derivative tells us the slope of the tangent line. Okay. So let's try an example and calculate it. We're going to calculate the derivative given a particular function. And so this will then tell me my slope of the tangent line at any point. So what I want to find this derivative is I need to take the limit as h approaches 0 of f of x plus h minus f of x divided by h. That is our difference quotient. So utilizing our function, I've got to go ahead and plug x plus h in for x, which is not pretty. This gives us the limit as h approaches 0 of x plus h squared minus 4 times x plus h. And then we want to subtract our original function, x squared minus 4x. Then divide this quantity by h. Okay. So this gives us the limit as h approaches 0. Gotta FOIL this thing out, unfortunately. X plus h squared will give you x squared plus 2xh plus h squared. Distributing the minus 4 gives you minus 4x minus 4h. Distributing the minus gives you minus x squared plus 4x divided by h. So we get some nice cancellation, x squared and negative x squared. Then we've got negative 4x, positive 4x. And so we're left with the limit as h approaches 0 of 2xh plus h squared minus 4h divided by h. Okay. Now everything in here has an h in common. So again, we can do some cancellation. This will completely disappear, which is what I want because this is a problem in the denominator. This h is completely gone. This h is completely gone. One of these is gone. So this becomes the limit as h approaches 0. We're left with a 2x, a positive h, and a negative 4. Now 0 problems, if I plug in h equals 0, it doesn't cause me to divide by 0 anymore. So no issues plugging this in. That's 2x plus 0 minus 4, which gives us 2x minus 4. Okay. So this is what I'm defining to be my derivative function. But now if I want the tangent line at 5, or x equals 5, I could just plug it in here. So I no longer have that same issue anymore of having to go through individual ones. So this now gives us the slope of the tangent line at any x value. And it saves me from constantly re-going over this limit. So this derivative results in a function, but tells me information about my graph itself. All right, let's try a second one. There's a select group of functions we can go through this limit process for. Otherwise, it gets really disgusting and tedious. Square roots are one of them. So we're going to find the derivative of the square root of x plus 7. Now, to also make my life a lot easier, I'm not going to write this limit. I'm going to start by just figuring out what does this difference quotient boil down to. Because I'm lazy, I don't like to write limit over and over and over again. We need to simplify this. If I plug in x plus h in here, that's going to give me the square root of x plus h plus 7 minus the square root of x plus 7. And then divided by h. Anytime you go through a formal definition, you want this h in the bottom to disappear. So the trick we have for square roots is you want to multiply by the conjugate. Okay. And so the conjugate of the square roots is you write exactly the same thing underneath the radicals, but you change the sign from negative to positive. And I can't just do this in the top. What I do to one, I've got to do to the other. So we've got to multiply by the same thing in the bottom. But the nice thing is, when we now go through and FOIL this numerator, you get your first term, which they're exactly the same thing. So I get a square root squared. So my first piece gives us the square root of x plus h plus 7 squared. The outer would be positive, this square root times the other. The inner is the same thing, but negative. So when you multiply by the conjugate, the outer and inner cancel. And then our last terms would be negative square root of x plus 7 times positive square root of x plus 7. So overall the sign is negative, and you get that square root squared. Okay. And then in the bottom, I'm going to have h, and I'm going to have this expression. Not going to distribute that out. Okay. But now we take a square root and square it, cancels out. Same thing, the square and square root cancel, but that minus sign has to be distributed to the contents inside the parentheses. But thankfully, we get lots of cancellations. So I've got a positive x, I'm going to subtract x. Positive 7 minus 7. All that is left is an h in the numerator and an h times all of this in the denominator. So again, we got more cancellations. H divided by h, those disappear. So now I've got a simplified expression for my difference quotient. This tells me my derivative is the limit as h approaches 0 of this difference quotient. Which we have already simplified. So I'm left with 1 and then these square root expressions in the bottom. Okay. And now we have 0 issues plugging in h is 0 here. So this gives us 1 divided by the square root of x plus 7 plus the square root of x plus 7. So we get 1 divided by 2 square root of x plus 7. So you could absolutely, if you want to, jump into taking the derivative right away, but just be careful. At every step along here, you would have to write limit, 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 limit as h approaches 0, because you can't drop that until you actually take the limit. So be careful with your notation, which is why I just simplified this first. Okay. All right. So realistically, we have a ton of different ways to talk about this derivative. It really depends on the context of the problem, which notation you're going to use. But if you have y equals f of x, then the derivative can be written as y prime, so we use that prime notation. You can also write it as dy dx. So this is called Leibniz notation, after a mathematician Leibniz. This d over dx tells you you're taking the derivative with respect to x. The y indicates the function you're working with. You can also say df dx, or you can say you're going to take the derivative with respect to x of this function. Some other notations that aren't as common that we're not going to use, we will use a lot of these though, is you use a capital D to represent a derivative, or you can use a capital D with the subscript of the variable you're differentiating. So if you have to go on to Calculus 3, you're going to learn about multivariable functions. In that case, that's where this kind of plays a role with what variable you have in the bottom, because you'll have functions of x, y, and z. You'll have variables that range into like 5, 6, 7 variables. So you have to be careful with everything going on. Now, if you want to say you're going to evaluate the derivative at a particular number c, we have a few ways to write it. The easiest one is you plug in c into this function. So plug in 3, plug in 4. When you're working with these notations, it's not as easy to indicate we're going to evaluate it at a point. So what we tend to do is use a bar to mean we're evaluating. So I'm taking the derivative with respect to x, I'm evaluating that at c. Or you can use a kind of square bracket. Bar and bracket both indicate the same. Okay. All right. So we've dealt with continuity, and we've learned that not all functions are continuous everywhere. Same kind of thing applies to differentiability. So a function is differentiable at a point if the derivative exists. It can be differentiable over its entire domain. It might be differentiable just on a select group of things. It might be differentiable everywhere except a point. So we have to kind of come up with, how do we know if a function is differentiable or not? And so we're going to start with a prime example of one that is annoying. We're going to work with an absolute value function. We want to see, is this absolute value function differentiable at 5? Okay? So anytime you're dealing with absolute value functions, you want to work in that piecewise form. So you want to remember, if I'm taking the absolute value of x minus 5, it will give you x minus 5 if x minus 5 is greater than or equal to 0. You have to change the sign if that thing is less than 0. So ultimately, this is telling you get these two different pieces if x is greater than or equal to 5 or less than 5. So here, if I'm greater than or equal to 5, that's what's happening on the right. When I'm less than 5, it's what's happening on the left. So we want to find, what does the derivative look like from the left and right of this number? So we'll start with the right, which means I'm using that first piece. I'm on the right of 5. I'm bigger than 5. I'm getting exactly x minus 5 in return. Okay? So to do that, we want to find the derivative. So we're going to take the limit as x approaches 5 from the right of the difference in our function in 5 over x minus 5. So this is equal to the limit as x approaches 5 from the right. Our function has output x minus 5, and we're going to subtract when we plug in 5, which gives us 5 minus 5, or 0. And in the bottom, we have x minus 5. So this is equal to the limit as x approaches 5 from the right of x minus 5 over x minus 5, which is the limit as x approaches 5 from the right of 1. On the right-hand side, it looks like our derivative at that point would equal 1. But for this derivative to exist, the overall limit has to be the same. So I need to see what's happening to the left of 5, which is where we're going to use this bottom piece. So I really want to do exactly the same thing, but now I want to approach 5 from the left. So we want to take the limit as x approaches 5 from the left of our definition of the derivative at 5. And the only difference from the last limit is this is negative x minus 5 now. So this gives us the limit as x approaches 5 from the left of negative x minus 5 over x minus 5, which gives us the limit as x approaches 5 from the left of negative 1. We get negative 1 on this side. Okay. So ultimately, since the derivative of the function at 5 is this double-sided limit, the function can't be differentiable at 5. Because the left and right hand limits are not the same. So when I evaluate this limit from the left, I get negative 1. From the right, I get 1. The overall limit doesn't exist, so my derivative does not exist. Okay. And ultimately, what you can kind of do is think of this picturely. The derivative is representing the slope of the tangent line. So for that derivative to exist, I better have a unique tangent line. Well, if I go to look at my absolute value of x minus 5, it's just our absolute value shape. On the right-hand side, if I pick any point, the slope of this tangent line is just going to be 1. The slope on the left-hand side is going to be negative 1, because they are just lines. At 5 itself, I can draw a bunch of lines that just touch that point. So there's really no unique tangent line at x equals 5. So that derivative cannot exist there because I don't have a set slope, because I don't have a set tangent line. So that's why it's not going to exist. But if I just gave you this problem, you probably wouldn't think about going through this process on your own. So why is it special that this happens for this function? And how do I know for other functions whether or not they're always going to be differentiable? Because here, I've got continuity at this point. I can draw right through it, but really we make this really sharp turn. So that's going to be one of the ways that we ultimately fail to be differentiable. The other thing that we need is we have to have continuity. I have to be able to draw a tangent line. So that means I have to have a nice smooth curve through that point. So differentiability is really strong. If your function is differentiable at a point, then you're guaranteed it's continuous there. So it's really strong. The reverse is not true. So we absolutely need a function to be continuous for it to be differentiable. But just because it's continuous, you can't say it's differentiable. This being a prime example. This function is continuous at 5, but I do not have a unique tangent line there. So it is not differentiable. So one way that we can fail to be differentiable is we can have a corner in the graph. So I don't have a unique tangent. Another possibility is that when you go to take this derivative and you try to plug in that value of c, it blows up to positive or negative infinity. So that's when you have a vertical tangent, because the vertical line does not represent a function. So ultimately, there are 3 ways that a function can fail to be differentiable. The first one is we have a corner, just like in our absolute value function. You make a sharp turnaround, you do not have a unique tangent line here. I have a ton, so my derivative does not exist. Second one is your function has a discontinuity. So here, how can I draw a tangent line if I don't even have a nice curve? Again, it lacks that uniqueness. And the third is the hardest one to really visualize. It's a vertical tangent. So the idea is if I were to find the tangent line at this point, it is a vertical line. So the slope is infinite. It's undefined. So the derivative is undefined. Okay? So we really want to get good with this connection. We really want to identify that if I have a function, its derivative is telling me information about tangent lines and what the slope of the tangent line is. We're going to see other applications of it really soon, but it's ultimately helping us know information about the graph, and it's helping us know about rates of change. So we're going to try a few examples. We're going to be given the graph of a function. We want to utilize that to sketch the graph of its derivative. So we're starting with this function, 2x minus 1. No matter the point you take on this line, if I go ahead and try to find a tangent line here, it is the line itself. Tangent line here is the line itself. So the slope of the tangent line at any point you try is 2, because it's a line. So immediately my derivative is always equal to 2, because every single slope at every single point is 2. Okay? So let's try now with a parabola. We'll make it have a little curve to it. If I look over here and I pick just a few points to get an idea, no matter what happens, if I draw the tangent line so it just touches my curve, that slope is going downward. So my tangent line has negative slope. It should be negative values. But you can see the slope gets smaller and closer to 0. So it gets more horizontal. If I pick a point here, that slope is a lot less than its prior ones. So ultimately, the tangent line has negative slope, but it gets closer to a horizontal line as I get close to 0. At 0 itself, if I draw the tangent line, it is flat. So at x equals 0, the tangent line's flat. So the derivative evaluated at 0 is 0. There's no slope. And then if I pick points to the right, I've got a positive slope and steeper, positive slope and even steeper. So the tangent line is positive, which means it's a positive number, and it's going to be getting bigger and bigger and bigger and bigger. So utilizing this to create a graph, at 0, my tangent line is flat, so it's 0. My slope is going to be negative for negative values of x. And then my slope gets positive for positive values of x. So here the slope's positive, here the slope is negative. Okay. So this connection is going to be really important to us. In terms of this limit process, we're not going to utilize that a ton, so we're about to start different rules that are going to help us out. But this is formally where it comes from. That connection we made, the very first section, told us information about the tangent line and secant line, and I just needed to let x approach c. So I took that limit as I got closer and closer. So that process is really important for us because it's how we're going to build on everything. And we're going to now come up with different ways to actually calculate derivatives, because we definitely don't want to sit here and do this over and over and over again. And we don't want to sit here and have to run through and calculate these square roots over and over and over again. So we're going to learn tons of techniques very soon.